topic 15 basic physics, no? An engineer should know. It's not only electrical engineer, no? Okay, so there are 15 things, no? Atoms, electrons, protons, and others, isotopes and atomic weights, ions, compounds, molecules, conductors, insulators, resistors, semicon, current, static electricity, electromotive force, and lastly, non-electrical energy. So you should know all these things, to understand what really a circuit is, no? So yeah, we encounter these things, no? Not only in this case, no? We in our life we see many stuffs, no? When we have a paper and then we put our hands in the table and on top of the paper, and then when we together with our hand, no? So gravitation is a phenomenon that is identified as a force that acts on an all object with mass. Okay, so the study of electric force and which acts on all objects with a properly called charge. Okay, the electric force is much stronger than gravity in most systems where both appear. Okay, so gravitation, we've learned this one in classical physics, and now it has a similar phenomenon in the modern physics, which is the electrical force. Okay, because of the charge. Okay, so in the first atoms, so we have all matter was composed of particles that came to be called atoms. Okay, so now the electric force helps bind atoms together, so it is of fundamental importance in matter. So there's between atoms there's a force that unites them, no? And that electric force is very strong. Okay, very strong, and so that binds atoms together, no? So and then a simplified so this one is an example of a simplified model of an hydrogen atom. So you can see the nucleus, which is the center, and in the nucleus we have the protons and then the electron cloud. Okay, now it's a misconception that the electron are just a point in the cloud, no? But actually this is the case of the quantum physics, no? So the electron can be in this part, no? This part. So there's no such time that you can identify where the electron is. Okay, but Niels Bohr's they have some different. There are many models of charge. There are many models of an atom. Okay, so this is one of an example. So some famous representation is when you have an electron here and then electron. Okay, but that really doesn't represent the reality. But for the representation, for the sake of understanding, okay, the principle or the concept, so this one is very good, no? A simplified model. Okay. Then second, so electrons are negatively charged particles, first discovered in 1897 by an English physicist, J. Thomson, when studying what was known as cathode rays. Okay, so it was during the discovery of cathode rays. Okay, that electrons. Okay, so this is basically the start of the modern physics, no? The discovery of atoms and electrons. So they see, no, the importance of it. Yeah, so that's what we have said, because of the electricity, no? So third, protons, neutrons, and atomic numbers. So these are three different terms, and I know for sure you know why the protons are inside the nucleus or within the nucleus and the electrons are outside. So the basic idea is that the protons are heavier than the electrons. Okay, so that's why electrons are outside. Okay, they roam around. You can imagine in the world, so the protons are the rocks, while the electrons are the air molecules. Okay, so you can think that way, no? So the electron can move around, no? And in the universe is identical to every other proton. Neutrons are all alike too. Okay, the number of protons in an element's nucleus, okay, we call it the atomic number. That's what we call, no, the number of protons in an element's nucleus we call atomic number, gives that element its unique identity. Okay, for example, this is the carbon atom composed of 6 protons and 6 neutrons. For different elements, it can be 5 protons, 5 neutrons, no? Okay, as in hydrogen, the surrounding 6 electrons that do not have definite locations, and so can be a sort of cloud surrounding the nucleus. Okay, so yeah, so you have proton, neutron, and electron cloud. So you understand what is atomic number already, no? And so that gives the unique identity for an element. So the number 4, isotopes and atomic weights. Now, differing numbers of neutrons results in various isotopes for a given element. So we should put in mind or take note that the protons and neutrons are usually the numbers of neutron and proton, okay, should most of the time are the same, no, are equal. Now if they have differing number, then we call this one isotopes. For example, heavy hydrogen, whose atoms contain a neutron or 2 in nucleus along with the lone proton. Okay, so then we have atomic weight of an element approximately equals the sum of the number of protons and the number of neutrons in the nucleus. Okay, so that's the atomic weight of an element approximately equals the sum of the number of protons and the number of neutrons in the nucleus. So okay, so that's a simple chemistry in that sense, no? Then we go to the ions. An atom that has had the charge altered in this way is called an ion. Okay, ion. So isotopes. So that's a general term, and then ion is the term we use for atom, no? So positive ions have had electrons removed, whereas negative ions have had excess electrons added. Okay, take note, negative ions have had excess electrons added. So you might remember taking a how you call it, the drinks, no, the Gatorade or Pocari Sweet, no, so they have positive ions. It's not that case, no. So that so some scientific facts on that, no. Okay, so we use this term to describe molecules that are not electrically neutral. Okay, so yeah, they're not electrically neutral. So we will see it later, no. So for example, yeah, so the carbon atom, and also for that. So this is an example of that, no. So we encounter things like this, no. So so this one attracts the other because of the ions, no, because of the positive and negative, and excess or lacking of charges, no. So that's it. So compounds, atoms of 2 or more different elements can join together by sharing electrons, forming a chemical compound. Okay, so we call this one compound or chemical compound. One of the most common compounds is water. So we know water has 2 hydrogen atoms and readily shared single atom of oxygen. Then molecules, when atoms of elements join in group of 2 or more, we call the resulting particles molecules. Okay, so when they join together, so molecule. So this is the molecule for the solid, this one is for the liquid, and this is for the gas, no. So 3 different states, no. So molecules, so atoms of elements join in groups of 2 or more, we call the resulting particles molecules. Okay, so then we have conductors. These wandering or free electrons are called conduction electrons or conducting electrons. Okay, so when the electrons travel from one atom to another, okay, We define an electrical conductor as a substance in which the electrons can move with ease. Okay, so electrical conductor, so there's no the electrons can move with ease, no? So we call that material or substance electrical conductor. Then copper is therefore an excellent conductor, okay, of electric charge. So now in insulators, okay, an insulator prevents electron movement from among atoms except occasionally in tiny amounts. Most gases make good electrical insulators. For example, air. Air is a good electrical insulator. Charge cannot flow along or through an insulator, so its electric forces remain for long periods of time. Okay, so we can so there's a blockage, no? So we know the most common insulator is like a plastic, no? So really, the electron cannot transfer, no, to the other. Okay, two charged materials are insulated by air. So positively charged glass rod, and then the neutral conducting sphere with charge distribution. But without physical contact, why there's a change in charge distribution? Okay, why is it there's all negative here and then all positive? Okay, even if there's no transfer of electrons or charges, no? So this is what we call the induction. Okay, we will discuss this one later in the later topic. Okay, so but you can see here that the charges doesn't that the charge does not transfer from this metal rod to the conducting sphere, okay, because it is insulated by air. Resistors, okay, so are materials, okay, they can resist the flow of charges, and the measure of how much a material resists the flow of charge is what we known as resistivity. Okay, so the materials that exhibit resistivity, what we call resistors. Okay, so resistance, but there's a specific topic for this wherein we will find out that resistors are not just an undesirable phenomenon, but actually it has a good effect, no? It has a good impact, no? As the conductivity improves, the resistance decreases. Okay, so it's inversely proportional. Then 11, semicon. In a semicon, electrons flow easily under some conditions and with difficulty under other conditions. Okay, so semicon are sometimes conductor, sometimes insulator. Okay, so that's the case, no? So that's the idea of some of our switching devices. Okay, so later we will talk about this, the hole motion, and so the hole is like the lack of electron, so it will just transfer. So we can take of that one, but we just think of the electron motion. Okay, materials engineers treat the materials so that they conduct well some of the time and poorly some of the time, and this is the principle of diodes, transistors, and integrated circuits. So of course it's part of our smartphones and computers. Okay, so that's semicon. We have conductors, insulators, and semicon. Okay, so these are the three major classification of materials. Okay, and we have the current. So current is the flow of charge. Okay, so the rate of flow of charge is what we call current. An ampere is the flow of one coulomb of charge through an area in 1 second. Okay, a current of 1 amp would result from 6.25 times 10 to the 18 electrons flowing through the charge A each second. Now this one is one charge, no? One coulomb, and this is the number of electrons in one coulomb. So important to take note that 1 amp is equal to 1 coulomb of charge over an area. So let's say 1 meter squared. Okay. Now the charge can be expressed in electrons, so 6.25 times 10 to the 8, 18 electrons. But since this is a big number and it's not practical to use this one, so that's why we have this one column of charge. Okay, so then later, so I is actually dq over dt. Okay, so we will talk about it later. Okay. So now we have the static electricity. Static electricity is a buildup of electric charge on the surface of an object. The arrangement of the charge remains constant or static. So there are many examples. So we have Van de Graaff generator. So you have a motion here, okay, and then it creates friction, and then it changes the charges here in the metal sphere. It becomes more positive, okay, because of the friction due to the belt. Okay, and then this is driven by a motor drive. Okay, so you will find, you can search this one in the YouTube if you want, and you see that when you put your hands here, your hair will stand, no? So your hair, because of the positive charge. And another example is when the building up of electric charges in the clouds, no? So we have this simple example. So more negative in the clouds and more positive in the ground. And we have electromotive force. It's not a force at all. So what then is EMF, and what is the source of EMF? So EMF, a source EMF maintains one terminal at a higher electric potential than the other terminal, acting as a source of current in a circuit. When the EMF source is not connected to the lamp, there is no net flow of charge within the EMF source. EMF is measured in units called volts. Okay, actually an effective EMF is what we call volts. We will still review this one in later class. Okay, so but it's good to understand that EMF is not a force, but it's a voltage, no? It's a potential difference or between for example the positive and the negative. Okay, so it's the imbalance of charges, no? Because of this imbalance, so you have two levels. You have the level, so the higher level and the lower level. Okay, it's like a wave, no? Like a wave, no? So you have here, and then you have these two levels. So this level is what we call the EMF or the voltage, no? So this is more positive and then less negative. Okay, so and then it turns because of the our system tends to be in equilibrium, so then this voltage changes in that way, you know? Okay, so we will talk about this later. Okay, but the important thing is that the higher potential and then the lower potential. So if there's no difference, then there's no electric current, no? So there's no current flowing. So if the same amount of, if there's level positive, then there's no movement, no? There's no movement here. And then you can see the different sources of EMF. So we have wind, and we have tidal hydro power plant. Then so there's also a flowing or falling water hydro power plants. Okay, then we have the solar plants. And then we have the batteries, no? Batteries are so some of it are non-rechargeable and some are rechargeable. Okay, now there are non-electrical energy terms, no? In scientific experiment, we often observe phenomena that involve energy in non-electrical form. For example, the visible light, no? Generated by lamps. Okay, then also the heat energy in the electrical heaters and other devices. And we also have conversion of electricity and radio waves or UV rays and X-rays. Conversion of electricity into mechanical energy, so mechanical energy, no? Then we have magnetism, so what we call the electromagnetism. And then we have dry cells, wet cells, and batteries. Okay, convert chemical energy to electrical energy. So there are some energy that you might interchange with electrical energy. Okay, but there's no problem. They can be converted into electrical energy. Okay, for example, mechanical to electrical or chemical to electrical. So in that way, we can transfer the energy from one place to another. Okay, so these exciting works can be specialized by an engineer. So any of these, no, actually we can for those EE, so you can actually specialize in these some of these fields, no. Okay, so these are the things that you have learned today.